Congratulations on finishing your first couple of C programs. I know that your first foray into C syntax can be daunting, but I assure you, at the end of the course, you'll be able to look at the first couple of assignments and complete them in minutes. Now that you're getting more familiar with syntax, let's get to Caesar. In Caesar, the user will submit an integer key as a command line argument, then enter a plain text message at the prompt. The program will then encipher the text and print their ciphertext message. The enciphering process for Caesar is quite simple. Shift each letter in their plain text by the key. As a result, it's also pretty insecure, but implementing Caesar will introduce us to ASCII Math and array data structures. We'll get to more complex ciphers later. With a Caesar key of 2, the letter A in plain text would be represented by the letter C in ciphertext, because C is 2 letters after A. B would be represented by D and C by E. Towards the end of the alphabet, W is represented by Y and X by Z. But Y doesn't have 2 letters after it, so the cipher wraps around the alphabet. Y in plain text is thus represented by A in ciphertext and Z by B. It may help to view the Caesar cipher like a continuous alphabet wheel. To encipher their text, the user will enter 2 arguments into the command line, /Caesar, followed by a key. As always, we can't trust the user completely to enter input that makes sense for our program, so we'll have to validate their command line input. Instead of using int main void, we're using int main int argc string argv. The integer variable argc represents the number of arguments passed into the command line, and argv is an array, or think of it as a list, of the arguments passed in. So for Caesar, how do we validate the user's input? Well, they should only be entering 2 command line arguments, /Caesar and a key. So if argc isn't 2, that means that they either forgot a key and just entered /Caesar, or they entered multiple keys. If this is the case, then you'll want to print instructions and quit the program. They'll need to try again from the command line. But even if argc is 2, you'll need to check whether they gave you a valid key. For Caesar, you need an integer, but argv is an array of strings. How do you access that key? A quick look at arrays, data structures that hold multiple values of the same data type. Entries are 0 indexed, meaning that the first element is at index 0 and the last element is at index size -1, where size is the number of elements in the array. If I declared a new string array mailbox of length 3, visually it looks like this: 3 containers for strings side by side. To access any element, you type the name of the array and then indicate the index in square brackets. Here I'm assigning a value to each element, just as I would do with any other string variable. So, to access our command line arguments, all we have to do is access the right element of the argv array. If the user entered /blastoff team rocket into the terminal, argv0 would be /blastoff, argv would be team, and argv2 would be rocket. Now that we can access our key, we still need to make sure that it's correct. We need to convert it into an integer, but we can't just cast like we've done previously. Luckily, the a2i function takes care of this for us and even returns 0 if the string can't be converted into an integer. It's up to you, though, to tell the user why you won't let the program proceed. Store the result of a2i in an integer, and there you have your key. The next part is simple. Prompt the user for their plain text, which will be of data type string. Luckily for us, all user inputted strings are valid. Now that we have all necessary input from the user, it's time for us to encipher their message. The concept of Caesar is simple enough to understand, but how does our computer know which letters come after one another? Here's where the ASCII table comes in. Every character has an integer number associated with it. Capital A is 65, capital B is 66, lowercase a is 97, lowercase b is 98. But characters aren't limited to just alphabetic numbers. For example, the @ symbol is ASCII number 64. Before dealing with the whole string, let's pretend we just have to shift one character. Well, we only want to shift actual letters in the plain text, not characters or numbers. So the first thing that we'll want to check is whether the character is in the alphabet. The function isAlpha does this for us and returns a Boolean, true if the character is a letter, false if otherwise. Two other useful functions are isUpper and isLower, with self-explanatory names. They return true if the given character is uppercase or lowercase, respectively. Since they're Booleans, they're useful to use as conditions. If isAlpha returns true, you'll need to shift that character by the key. So let's open ASCII Math and do some ASCII Math. The usage is very similar to the usage for Caesar and takes in a key at the command line. If I run ASCII Math 5, it seems to add 5 to A, giving me the letter F and displaying the ASCII value. So let's take a look at the program. You might wonder right here why letter is an integer when it's clearly, well, a letter. It turns out that characters and integers are interchangeable. By putting the letter A in single quotation marks, the integer can store the ASCII value of capital A. Be careful though, you need these single quotes. Without the single quote marks, the compiler would look for a variable named A and not the character. Then I add letter and key, storing the sum in the int variable result. Even though result is of data type integer, my printf statement uses the %c placeholder for characters, so the program prints the character associated with the integer result. And since we print the integer form as well using %d, we see the number as well. So now you can see that we treat characters and integers and vice versa. Let's test out ASCII Math a few more times using 25 as a key. We get the letter Z. Now, we try 26. We want to get the letter A, but instead, we get a left bracket. So obviously, just adding the key to the letter won't do. We need to figure out a formula to wrap around the alphabet, like our example in the beginning did. A formula for the Caesar shift is as follows. C equals P plus K modulo 26. Remember that modulo is a useful operation that gives us the remainder of dividing one number by the other. Let's apply this formula to the plaintext letter with A key of 2. The ASCII value of Y is 89, which gives us 91 modulo 26, which equals 13. Definitely not the ASCII value of A. Humor me now and move away from the ASCII values to an alphabetical index where A is 0 and Z is 25, meaning that Y is 24. 24 plus 2 modulo 6 gives us 26 modulo 26, 0, which is the alphabetical index of A. So this formula seems to apply to the alphabetical index of a letter and not its ASCII value. But you start with ASCII values, and to print the ciphertext character, you'll need its ASCII value as well. So up to you then to figure out how to switch back and forth. Once you figure out the right formula for one character, all you need to do is apply the same formula to every letter in the plaintext, only if that letter is alphabetical, of course. And remember that you need to preserve the case, upper or lower. That's where the isUpper and isLower functions mentioned earlier will come in handy. You might have two formulae, one for uppercase letters and one for lowercase. So isUpper and isLower will help you determine which formula to apply. How do you apply your formula to every single character in a string? Well, a string is just an array of characters, so you can access each character by looping over every character in the string in a for loop. As for the condition of your for loop, the function strlen for string length will come in handy. It takes in a string as input and returns the length of that string. Make sure to include the right library to use the string length function. And there you have your ciphered text. My name is Zamila, and HivWig, wig QG50.